Smojo basics, right? So I've already told you guys to complete the SM101. I think some of you don't have the username and password yet. Once you fill in the form, then Chris will send you the stuff, send you the details, right? But that SM101 will contain a lot more detail than what I'm talking about today, in the sense that they'll cover more functions and so on. What I want to do today is just to cover the gotcha parts. Maybe the parts in which you might trip you up, especially if you come from a C++ or Python or a Java kind of background, okay? Because Smojo is very different from other languages, okay? But fortunately, it's not, the differences are good in the sense that it actually makes your code shorter and easier to write. Okay, so we'll cover a lot of stuff today. I think, I know I said it will just be an hour previously last week, but I think an hour and a half might be more comfortable. Okay. All right, so let's just dive into it. So here we see a very simple Smojo program. Okay, it's the Hello World program. Those of you from Java or Python, we might see this, or programmers might see this quite often. Okay, so Hello World is just Hello World, the string Hello World, followed by a dot. And there must be a space between the string and the dot. Okay, so Smojo, unlike other languages, is not right to left. It's left to right. Okay, so whatever is left comes first, and whatever is right comes afterwards. So the way to read a program like this is to say, I've got hello world, the string hello world, and then I want to print it using the dot function. So the dot is actually a function or a word. Okay, so in Smojo, we call those functions words. All right, so the hello world is a string literal. Okay, and the dot is a word that just prints that string literal to screen. All right, so in Smojo, there are just two kinds of things. There's just literals and words. There's no punctuation at all. So a lot of the stuff that you think it's punctuation is actually not punctuation. It's most likely a word. All right, so a semicolon or a colon, or even a comma or a full stop, they're not punctuation, or brackets, they're not punctuation. They're all functions, okay, or words. Right, so remember, in Smojo, everything is very simple, left to right, and everything you see is either a literal or a word of some kind. There is no punctuation at all. Okay. And unlike Python, where indentation is very important, in Smojo, indentation is not important, but spaces are very important. Okay, so the way Smojo knows what is a function and what is, let's say, something else is by using spaces. Okay. All right, so let's analyze a very simple program. Okay, and the program is 1, 2 plus dot. Okay, so I'm sure you can guess what this function does, or sorry, this program does. Okay. Now, literals, which I will by convention color green throughout this lecture. Okay, literals put themselves onto something called a stack. Okay, I'll show you what a stack is later on. And words consume the literals off the stack, and then maybe if they want to return a value, they'll push one or more values onto the stack, or maybe nothing at all. Like the print, for example, will not put anything onto the stack. Okay, because it just prints it out to screen. Okay, so let's analyze that very simple program, right? So when you have the 1, all right, remember the program was 1, 2 plus dot. So as soon as you get the first 1, when the program is run, it immediately puts 1 onto the stack. Okay, and when you put the number 2, when it encounters the number 2 next in the text stream, then 2 is placed on the stack as well. So you got 1 on the bottom part of the stack, which is on the left, and you got 2 on the right, okay, which is the top of the stack. Whoops, sorry. Oh, I'm pressing the wrong button, sorry. Okay, so 1, 2 plus gives you the 1, 2 on the stack, okay? The plus will remove both 1 and 2 simultaneously, okay? And then it'll place a 3 on the bottom of the stack, all right? And the dot, you might have guessed, removes the number 3, prints it to screen, and of course, then at the end of the program, you're left with an empty stack. Okay, or rather the stack in the same condition as it was before. Now, your Smojo stacks right now, we've set the stack size. In the early versions of Smojo, the stack size was infinite. It was just the number of, what is it called? Elements in your amount of RAM you have in your computer. But the newer versions of Smojo have smaller and smaller stacks. So the one right now has got a stack of about 512. All right. So once you exceed that, it will give you an error. Okay, but you should never have programs which use a stack so much or so much of your stack. Okay, so 512 actually is very generous. I might actually reduce it further in the future. Okay, but that's really how the simple Smojo program works. All right, so let's take a simple word instead now. Let's say we're trying to find the average of two numbers. Okay, so I'm sure you've seen things like this, where you've got the body of the header and maybe the tail of the function itself, of the word. Okay, I'll explain in detail what these things mean later on. But the body is what we're concerned about right now. So we want to add two numbers from the stack, all right? And then that's just a plus dot. Now we use a plus dot because the plus dot is for real number addition. So in other words, if I use a plus alone, it assumes that the numbers are integers or can be rounded off to integers. So 1.2 plus 2, right, which is a plus, an ordinary plus will give you 3. But a plus dot will give you 3.2, okay? Next, of course, for averages, you want to divide by 2. Okay, so again, we got 2, and instead of a slash, you put a slash dot because that's a real number division. Okay, let's just play this and see how it works on the stacks again. So at the start, the stack is empty. You put the 1, you have the 1. You put the 2, you got the 2. You have an average. Now, average, remember, is plus dot, which kills off those two, takes the two numbers, the two top elements of the stack, adds them together to give you a 3.0 because now it's a real number. You have the 2, so it puts 2 on the stack. So you got 3.0 at the bottom of the stack and the 2 on the top. And you have slash dot, which just does the division, but it's real number division. So you get a 1.5. Okay, so that's fairly straightforward, I think. All right, next, I want to cover something called local. So you can see here in this function, I've got no arguments. There are no arguments. The stuff in purple that you see, the funny n double dash n, it doesn't mean anything. Anything in purple by convention is a comment. It's not meant for the computer. It's meant for us as programmers to understand what are the inputs and outputs of your words. So in this case, I can instantly tell. So n by convention in Smojo means number. Okay, n means number. SEQ means sequence, etc. Right? And you come to know these things as you go, as you program more. So there are two n's. I mean, it means that average. This version of average at least requires two numbers. Okay, and the output is also a number. Okay, so it's a very simple way of writing. In fact, this is the best way to write this function average. But if you're more familiar with Python or Java or C++, you know that all the inputs must be bound to a name. So in this case, there are no names involved because you're just working off a stack, right? But in most languages, you need to bind whatever is passed into the function with a name. Now, you can do that in Smojo as well, but for this example, it becomes worse. All right, so in this case, I've bound the top two elements of the stack to names, temporary names, A and B. These names A and B are called locals, okay, or local variables as they are known in other languages. All right, so the bottom number on the stack, the lower number on the stack is bound to A, and the topmost element in this case is bound to B. Okay, but you can see clearly that this form, at least in this case, it doesn't look as clear as or short as the average function, the original average function. Okay, and it's actually slower as well. Okay, slightly slower. Okay, so much for the basics. So you know how Smojo works. You know how to create these words and so on. Let's go a bit deeper. Okay. So let's go back to our simple word again. The average word, okay? So you have average. Now, I promised you just now, or early on, that there is no punctuation in Smojo, okay? So this is true. The colon here is not punctuation. It's actually a function or a word. And the word does something quite specific. It does two things. The first thing is that it flips Smojo into something called compilation mode. Okay, I'll explain that later on or shortly. Okay, and it starts a new entry in something called the Smojo's dictionary. Right, so these are the two things, and we'll look at that later on. I'll explain that later on what it means. Okay, but you need to understand that it is not punctuation; it's a word. Okay, and the name average here is the name of the new word. All right, that we're trying to create. Now, I've already explained to you that this portion here in purple is really just a stack comment. It's ignored by Smojo. Okay. Then you got the plus dot, you got the 2 divide by, okay. And I've explained also that the plus dot and the slash divide by dot is, they're both real arithmetic. And you've got the semicolon. Okay, the semicolon, again, is not punctuation. It is also a function, a word. Okay. And what it does, it completes the dictionary entry and it exits compilation mode. Okay. All right. So what is this thing about the dictionary and why is it so important? It's extremely important that you understand this part about Smojo because, again, it's not something that is, how do I say, it's not present in other languages. Okay. So when we created the word average just now, what happens actually is that internally, there's a word average, or sorry, a name average, and it links to something called the body of the word itself. Okay, so the name and the body are separate in Smojo. In many languages like I said, Python or Java and so on, if you're familiar with those languages, the name is very tightly bound or tightly coupled with the body of the program. You don't talk like in Python, you don't normally talk about the function body being separate from the function itself and being used separately. Okay. So here, average is the name, okay, on the left-hand side. And the XT stands for executable, okay, is on the right. Okay, and we use XTs a lot in Smojo. Okay, they're one of the core parts of Smojo that you must understand. All right, and you can see that the plus dot and the slash dot are also actually XTs. I've called them by their names, but it's actually a reference to the XTs, okay, not the name itself. And here the literal 2 means that it's actually a function which takes the number 2 and shoves it onto the stack. Okay. So plus dot itself is a primitive word, and it actually is a bunch of Java code. You can actually, it's on the dictionary. Okay, it's compiled. And similarly for the slash dot as well, it's Java code. It's not Smojo code anymore. Okay, because Smojo, by the way, is actually built on top of the Java virtual machine, the JVM. Okay, so let's talk a bit more about executables, right? So the XTs is because it's executable. So XTs are, they are unique binary for the word itself. They are literals. In other words, they can be passed as a literal. And in fact, oftentimes we'll be doing this to actually pass these XTs into other words. We might be saving them onto disks, sending them over the internet, etc. Okay, so a lot of the power of Smojo is being able to treat these XTs separately from the function of the word itself. Okay, and you will come to see this later on. And they are unlike other languages, the XTs or what actually does the work is very loosely coupled or tied with the names. Right, so you can actually decouple it. You can change the definition quite easily of a name. So the names are they only exist in the dictionary and nowhere else. Okay, and you as a Smojo programmer can actually change quite a lot about where it looks for the names, what it does with the names, etc. You can change the default location of these names, and that actually makes Smojo very powerful. Okay, so you can overwrite the XTs, all right, using the colon or by some other means. And we'll see that also. So XTs are widely used in Smojo, especially in sequence transformation. So if you're doing the financial data engineering course, then you need to know this very well, okay? And of course, you're doing the other data infrastructure, the infrastructure development apprenticeship. This is also extremely important as well. XTs are a cornerstone of Smojo. All right, so now I want to just explain a concept called early binding. Okay, so let's say I've got these two functions. The first is called, two words. The first is called hello, and you can see from the comment that hello needs an input string and it doesn't output anything at all. Okay, and the second function is called greet, and greet doesn't take in inputs and it doesn't give you an output either. It's blank on both sides. Okay. If I call greet now, later on, towards the end, okay, so the first two, hello and greet, are compiled into the dictionary, but the last greet there is an execution of the word greet. Okay, so if you're familiar with Python, it's very similar in that sense. So when you run this program, you would see, in this case, hello Arnold. Okay, you can try it out if you have already access to your Smojo, to AutoCAD. Okay, let's change this a bit. Let's say instead now I redefine hello after greet. Okay, what happens then? Okay, so when I print greet out, do I see hello Arnold or do I see hello there Arnold? Which do I see? Can I get any response from you guys?
Hello there, Arnold.
Okay, you don't see, thank you for being brave, Keith. But you don't see hello there, Arnold. You just see hello, Arnold. Okay, and this is what I mean by early binding. Okay, so what happens is this: the version of hello that is used in greet is the version which existed at the time of creation of greet. So at the time of creation of greet, the version of hello is just hello, right? The first one. Okay, so when hello is overwritten, right, later, it doesn't matter, okay, because greet will use the old XT. Okay, this is guaranteed, and this makes the system very stable, right? If the definitions of words were to change, and then that will also change the behavior of greet, that will make a very unstable system. Okay, now let's go on. Is that clear, guys? It's clear, right? Okay. So I want to explain a bit more about interpretation versus compilation mode. Okay. So just now I explained that the colon word changes the system into compilation mode, and I also explained that the semicolon pushed it back to exited the compilation mode into interpretation mode. All right. So there are two modes in Smojo, just two: interpretation and compilation. In interpretation mode, all the words are executed as they are encountered. So when you see the early programs today, like 1, 2 plus dot, that is implicitly in interpretation mode, because the one is, as soon as it's encountered, pushes itself on the stack. 2, as it's encountered, there's an action. Okay, so as the interpreter reads the text, your source code, if it's in interpretation mode, it executes the function, or executes the word, or if it's literal, it puts it on the stack. Okay, very simple. So this is the default mode for Smojo. Okay, as the words are encountered or literals are encountered, some action is taken. In compilation mode, most, not all, but most of the words are not executed as they are encountered. Instead, they are compiled. Okay, they are not executed. All right. The exceptions are immediate words, which are always executed no matter what the mode is. Okay, so there are two kinds of words: the ordinary words, which have compilation and interpretation type modes, and there are immediate words where it doesn't care and it always executes. Okay, so let's look at this, the average function again. I'm sure you're sick and tired of it, but it can teach us a lot. Okay, so the colon begins compilation mode, and the semicolon exits compilation mode. Now think about it. If in compilation mode, the words are always compiled and not executed, then if semicolon is not an immediate word, it will also be compiled. It can't do anything. So you need to have these immediate words to do stuff like this, to do things, action, or take actions while the word is compiled. Okay, and this behavior is actually not so much useful for financial data analysis, but it's very useful for the other apprentices who are taking the infrastructure development course, apprenticeship, because this behavior allows something called meta programming or macros. Okay, so I won't go into it in this talk, I think, because it's not really applicable to most of you, but it's applicable to the other infrastructure development guys, right, and gals. All right, so another point, how about the purple bracket for the comment? Is that immediate or is it an ordinary word? So we know that the plus dot is an ordinary word, right? The colon can also be an ordinary word as well. It doesn't have to be immediate. To is obviously a literal. The slash dot is, of course, an ordinary word as well. It's not immediate, so it's compiled. Okay, but how about the bracket there? That's number one. And is how at the ends and the double dash, are they, and the close bracket, are they both words as well? What do you think? Well, since we don't compile those things, they must, okay, so before average, it's interpretation. During average, it's compilation. And then since we've exited, we go back to interpretation mode, right? And the answer to my is that this is an immediate word. What it does is that it immediately swallows all the text to the right of it until it encounters a closing bracket. Okay, and then it just discards it. Right, that's what that word does. It's an immediate word which swallows everything to the right and then discards it. Okay, and you can actually write it in Smojo. In fact, it is written in Smojo. All right, it's not a Java word at all. Okay, so I hope this gives you a better understanding. I think as you work through the exercises, this might come in helpful. All right, now we go to the more important part, is how do we get an XT from its name? Okay, so remember, the XT and the name are only linked in one place. It's in the dictionary by default. Okay, the dictionary. And so in interpretation mode, we use the tick to get the XT name. And in compilation mode, we use something called the bracket tick. Okay, so you will use these two words a lot in your Smojo code. So as an example, I've got the hello world program here again, but I've put it into a function instead. Okay, so it's not in interpretation mode anymore, it's a function. Okay, and if hello is run, all it will do is just to print out the words hello world. Okay, and if I want to get the XT of hello, I put the tick before it, tick space, then the name of the function, which is hello. Okay, so it gets the XT of the latest definition of hello. If hello were overwritten, it will only get the latest definition, nothing else, not the previous definitions. Okay. And this is the same thing for when you are using the tick, the bracket tick, which is in compilation mode. Okay. All right. Now we come to one other topic, which is very closely related to XTs, and that is quotations. So quotations are a way to make XTs without names. Okay. So with XTs, we separate out the name from the actual work, the function of the word itself. Okay, that's what an XT does, or is, okay? And so oftentimes we don't need a name for the function, okay? So in other languages, I think like Python, they call it lambdas, okay? But the Python lambdas are basically useless, all right? They're only allowed for, they're very restricted. In Smojos, we use these lambdas or quotations a lot, okay? So you need to know how to use them, okay? So like I said, quotations are very widely used in ordinary Smojo code. So for data processing and so on, whatever else it is, you can use these quotations and really cut down your code by a lot. Okay, so there are two forms for these quotations. The first form, which is not so often used, is this form here. So in this case, this is actually a function which you need to run it in interpretation mode, okay? And when you run it, it actually creates an XT and puts it on the stack. And that XT, if you run it or execute it, it will just print hello world to the screen. That's it, nothing else, okay? This is the same form, but wrapped in a function. So when you run myfunc, right, it will produce an XT on the stack. And the XT is exactly the same as what happened before. Okay, which is this XT represents something which prints hello world to screen. Okay, now I will pause here. Any quick questions? And I'll go for the online demo where I show you how to do something called numerical differentiation.
There are questions on the Zoom group chat, Anod. So I think Li Shuo just asked, what's the use of one-timer function?
They're not necessarily one timer, okay, because they can be copied, they can be sent out. Later on, you will see the utility of these functions, okay? Usually the so-called one-timer functions are created in other functions, okay? So you got a function which creates this function, and the output is a function, okay? So like in Java or in Ruby or in maybe even, I'm not sure, I think Python, you have got classes, okay? So but classes, you need to define those classes beforehand, etc. Okay, so in Smojo, we don't use classes as much. We use instead these lambdas, okay, very often, or quotations as we call them. Okay, they're extremely useful, and they're not a new concept. They're actually a very old concept. I will show you a lot of examples as we go on this evening. Okay, good. I'm actually not bad on time as well. All right, so any other questions?
There is. What are the difference between Smojo and Forth?
They're very similar. Okay, so I am the author of Smojo, and I learned Forth by accident very late. So a lot of the stuff that you see here in Smojo is based on Forth, but Forth doesn't do a lot of the stuff for data processing and so on. It doesn't do a lot of stuff that we need for networking and all the other modern conveniences, shall we say. Okay, and there are other differences as well, things like serialization, infinite sequences, laziness, and so on, which is very important for us when it comes to data processing. Okay, so I developed and designed Smojo for a few reasons. The first one is that it can be used by non-programmers. So actually to actually write this kind of code is really quite easy, quite simple. We've actually taught it to even kids, to be honest. Second thing is that it can do things like meta programming very well, which is actually something that is not commonly done. So I can't explain it to you because you probably haven't seen it. Okay, but if you're familiar with things like Lisp or Haskell, then you probably get a better idea where we're heading towards. But most people wouldn't have seen those things. But I hope, again, that it'll become clearer as time goes by. All right. The other thing is data processing. So we use Smojo a lot. In fact, it's used right now to process, I would say, about 100 gigabytes of data every day, at least 100 gigabytes of data every day. All right, because we run a weather forecasting company, which needs to actually do this, and it's been doing it for years. All right, so it's a very useful tool for distributed data processing. A lot of the stuff that comes out of the box makes a lot of these hard topics or hard things to do very easy. Okay, and I hope that's something that you can see as you experience the apprenticeship, among the other things. All right. Any other questions?
Is there a documentation somewhere?
Yes, there is, and I've already given you access to it. Anything else?
Hi, just a small question about the input and output types, and is there a special way to define them in the functions?
Okay, good question. So Smojo is a dynamically typed language, right? Like I think Python as well, right? So it's not statically typed.
Okay, yeah, that clears enough. Thank you.
Okay. Anything else?
I think we are good to go.
Yeah, I see your question, Yuran, on the chat. It says, isn't this hard coding? I have no idea what that means. But you want to explain that? Yuran, are you there? Okay, maybe he's facing problems with his mic or something. Okay, anyone else with a question? Chris, any other questions?
I think we are good. Or do we get the syllabus for these apprenticeships?
Yes, not now, but later on. Okay, so if that's this thing, I'll just give you a demo right now, okay? Because you see, guys, this stuff that it looks like a mixed bag of rubbish, okay, honestly. If you're not familiar or don't have the experience doing a lot of programming in different languages, it will not seem familiar, and you'll be thinking, why on earth are these a particular choice of features in this language, and what's the use of it, right? Why can't I just use my Python or Java or C++, okay? And I hope that within the next hour and a half, at least most of those questions will be answered. So you can see where we are headed towards, okay? And I hope that some of the examples might make things a little clearer, okay? But it still will require you to think a bit and try a bit yourself. All right, let's go to... Okay, I'm just fooling around just now. Okay, so the example that I gave was numerical differentiation. So I'm going to build this up a bit so you can just see what's happening, okay? So we're going to use a very simple, what's called forward differencing. So I'm not sure how many of you are familiar with, very simple, well, I'm sure all of you have done differencing before, right? Differences or differentiation, right? So differentiation is basically you got some function fx, right? You want to basically, do a tick, and that is roughly equals to, right? I don't have an approximate symbol out here, but approx, right? It's really f of x plus some, let's say epsilon, right? All right. Then I minus the f of x, and then I just divide the whole lot by epsilon. Oops. Okay. So that's called forward differencing. Okay, and it's actually not a good thing to do. It's actually numerically unstable. So you shouldn't do this in real life. There's actually better ways of doing it. But look, it's just an example. So let's say I've got a function f equals to sine x. So if you're familiar with basic, if you need some basic math when you're in high school or something like that, right? You know that f dash of x is just cos of x, right? Okay. Okay, so let's say you want to write some code to do stuff like this. Okay, so how would you write it? So let's call it d sine of x, right? And it's going to take a number n and return a number, right? Now, I don't, of course, since you already know that it's going to be cos of x, that's easy. But let's say it were a more complicated function. Okay, so what you would do is to say, look, I want to define, first of all, some epsilon. Let's say 0.001, right? Constant. Okay. And that defines a constant called epsilon, right? And so what you do is you'd say, I want to take, let's say, my x, whatever the x is. I'm going to bind it to this as a local. Okay. I'm going to say x. I'm going to add the epsilon. And I'm going to call sine. And then I'll say x sine. Oh, not sine. Okay. And then I want to subtract these. And then I want to divide by epsilon. Okay. And then I can test it out. Let's say 0.1 d sine. And I put 0.1 cos. All right, and I compare these two around this thing. I think my thing went to sleep. Okay, and you can see they are about the same to at least a few decimal places. If I increase the accuracy here, it gets a bit better. Okay, to about 1, 2, 3, 4, 5 decimal places. Okay, now if you keep increasing the zeros, it won't get better. It might get worse because of numerical errors and so on. So you shouldn't do that. Okay, but this is the basic idea of forward differencing. Okay. Now, what happens if I have a different function to differentiate, right? So what I have to do then is to create a new d something, maybe d cos, or maybe d some other function. That's silly, okay? Because I'd basically be writing the same code again and again, except for maybe this part here and this part here, okay? So obviously, I don't want to do this. It's silly. So I want to really instead have a general purpose differentiation. I call it diff, okay? And it's going to take not just a number, but also an xt, okay? So I'm going to bind this x and an xt as well. I'm going to call, instead of xt, I'm calling it functional f, okay? And here, instead of sine, I have the function. Because it's an xt, I'm going to execute the function. Okay, and I do the same thing here. All right, so now what I have is I have a general purpose differentiation, which takes in a number. I mean, where do you want to evaluate the differentiation, and the xt that you want to differentiate for. Okay, but here I need to change this because it's called diff now. Okay, and I need to pass it a function or an xt. All right, so I put the tick sign. Okay, so this is the first argument on the stack, which is 0.1 that goes into my x, and the tick x, the tick sign is my xt. It's the function. Okay, and this should produce the same answer as what we had before. Okay, see, it's the exact same function. All right, same answer. Okay. Now, that's all nice, but now let's say I become a little more, a little bolder, okay? You can actually shortcut this a bit. Instead of writing f execute is a pain in the right, to do that. So what I'll do is I'll first bind the f first, all right? So this binds the f onto the xt, but this tilde is special. It's a word which it's always matched with one of these brackets. And what it's doing is that it's taking that xt and giving it a name as a function. All right, so instead of a literal, it becomes a word again for a while. Okay, and the word is called f. So I don't need to put execute anymore. All right, but I need then to rebind the x as well. So I first bind the top part of the stack as a function and call it f. And the bottom part of the stack, or the lower part of the stack with the number, it's still x, my input. Okay, and I rerun the function here, and that's exactly the same thing. Okay, no change. Now, this is nice, But let's say I become a little more ambitious. I want to find, can I somehow reuse my diff or change my diff so that maybe diff gives the first order differentiation and diff gives the second order differentiation. Okay, is that possible? The answer is yes, but we got to change the way diff works. Right now, diff takes in a number and xt and gives a number. That's no good. Okay, because the inputs and the outputs are different. Okay, that's a problem. So when you write these functions for yourself, okay, note the kind of inputs and the kind of outputs that you have. Okay, if you want to make things composable, okay, is like what we are after really. You want to make sure that the input and the output are the same type. Okay, so what I want to do, I want to fantasize a bit. I want to say I have a diff instead, which takes in a function, any function, okay, but it doesn't output a number. Instead, it outputs an xt, okay? So I have to make some changes here, okay? Now, the first step is to wrap this up in a quotation. Now, this part might be a little confusing for you guys, but please bear with me, okay? So what does this diff do? Okay, so it takes in like my sign or what else it is, right? Okay, takes in my sign function, and it doesn't output a number. It outputs a function. Okay, so this is a function which creates a new function. So someone asked me, what is the use of the one-offs and so on? This is one of the use of the one-off functions, lambdas they call them. Okay, so don't think of it as one-off. Okay, that's a very narrow way of looking at things. Okay, you have to think of it as a lambda, which is a nameless function. And these nameless functions are extremely useful. Right, so this is one simple use case. There are actually many, many others. Right, so here I've bound the function that's on the input to a name called f, and I've created this new function which basically does numerical differentiation. Okay, so the output is the first order difference. So now, since the output is also a function, there's something called closure. This property is called closure. So you have an operator that takes the inputs and outputs the same type of output. So input and outputs are the same. They can be multi-valued, they can be single-valued, but they have to be the same type. Okay, that is called closure. Okay, and closure is it's a mathematical property which is very important. Okay, for operators, it makes them composable. Okay, so in this case, if I want to find the second order differentiation, I just put diff. All right, so the first function that comes in is this one, this xt. Okay, then this chap here, the first diff gives the first differentiation. Okay, it's difference once, and then calling diff again because of closure, the closure property, you get the second order differentiation. Okay, now will this work? Of course it won't work. It won't work because the function output is an xt. Okay, so what we got to do is, because it's an xt, I need to call execute. All right, so you can see it's a bit clunky to use. All right, so you only use it if you really have the need. All right, and knowing when the need and when it's not the need, that takes experience. Okay, so in this case, to use diff like this is extremely useful. So yes, there is a need. So let's just run this and see if it works or not. Okay. Okay. So here there's a problem. Okay, it says some kind of class casting. Okay, so the answer is because this x here is not bound. There's no, remember I removed the x from here, but you see this x is actually an input into this function instead, like that. Okay, remember from anything from here, this defines a whole new function. Okay, so let me run it again now. And you can see the answer is exactly the same. And we can try the diff, which is the, what's it called? Double differencing, all right? And that's the answer. Now, if you keep on doing this, because this numerical method is forward differences is not a good one, it's unstable, right? It will give you rubbish after a while. Okay, so you cannot difference infinitely. There are actually problems with the this formula here, but that's not a problem with our programming. It's really a limitation of our formula you put in. Okay, but this also means that you can experiment with different forms of diff, and it's just one function, right, to see which is more stable, which is less stable, etc. And it's actually very useful to swap around different differencing schemes, all right, so that you can actually try and maybe see which is faster, which is slower, etc. Okay, so I hope this simple example, and it's pretty short as well, gives you an idea of how all these concepts combine into a simple, concrete example. Okay, and of course, when you start working with some real life data and real life stuff, you'll see a lot more use cases. Okay, I'll pause here before I move on. Any questions?
Yes, I had left a question in the chat about there being a special syntax for loops in.
Yes, yes, there are loops and everything else. You can check the documentation if you want to, but yes, they are. Keith, so this lambda function is Smojo's way of doing a nested function. No, not really. A nested function is in most languages is a function within a function. Okay, this example that I'm giving you just now is not a nested function. It is a function which creates a new function and sends it out as an output. It's very different. Okay, I'll give you an example of a nested function. You can use quotations as a nested function as well. So let me give you an example. Okay, so let's say I had something like this. Okay, rarely in Smojo you use nested functions, but you can. So let's say my funct, right? Let's say it's doing nothing at all. Let's say I have, let's say an n here. Okay, let's say I bind the end to some x. Okay, let's say I put in something like this, x. Let's say I put a cube to it. Okay, so let's put x 3 like that. That's the cube. Okay, and here I can bind it to fn like that. So what this does is within this function, my function, I've created a temporary function called a cube of this thing. Now, if I just want to put a general purpose cube, I can just do that. Okay, I can call it cube. All right, and this would actually function like a cube. So in other words, x cube, right, would actually give you the cube of x. Okay, now so you can see it doesn't look good, it's clunky, and I would honestly discourage it. There are places that you will need to use something like this, but not at, I think, most of, maybe for the infrastructure development guys, yes, you would have to use something like this down the line. But for most of the stuff that you're doing for the financial data engineering, the answer is no, and I would discourage you from using it because it's hard to debug and it looks awful. Okay, so I wouldn't encourage nested function. So this is a nested function. It's not output anywhere. It's just for internal consumption. Okay, any other questions? No other questions? Okay, Erica asked a question. Why does Smojo, when you do 1 minus 1.2 minus 1, it returns a funny number, right? Okay, 1.2 1 minus dot dot. Okay, let's try that. Okay, so anyone wants to answer this question?
You want to enable share screen, Arnold?
Oh, my bad, sorry. Okay, can you see this? So 1.2, this is Erica Ko's question. 1.2 minus 1 will give you 1.9, not 1.2. Why is that? This is an important question. Anybody from a com science background or any experience with this kind of thing before?
Yes, it's because it has something to do with floating point error.
Correct. So when numbers are represented or floating point numbers are represented in a computer, they have got finite resolution. Okay. So they follow the IEEE, that's an IEEE standard, which all these languages all follow. The underlying engine for Smojo is just a Java engine, okay? And for most languages, probably all languages, you will get the same answer as well. Okay, so you've got to be careful with this. This is one of the problems of, or one of the difficulties in actually writing numerical processing, and why using real numbers or floating point stuff is tricky at best. Okay, any other questions? Chris, can you help me, please?
We are good on the chat.
Okay, so then let's move on. Yeah, so it's not that 1.2 cannot be represented by bits, and it's not quite that 1 is not exactly 1.000. It's that the choice of representation that is being used cannot represent 1.2 exactly, not so much the 1. Okay. All right, so let's move on. Let me just share this screen again. Okay, so let's move on now to something called sequence transformations. Okay, and this is really just the last half of the evening, and I hope that we can end maybe on time. Right, 1.5 hours. Okay, so I want, when you try and program in Smojo, in fact, at least the stuff that we're doing right now, you have to really change the way you think. There needs to be a shift in the way you think, and this is probably the hardest thing that I see most. If you're experienced in any kind of programming language, you'd have a problem with this. All right, there's a lot of pushback. Okay, but if you are a complete beginner and this is the first time you're programming, then you will have no problem at all. Okay, so those of you who have rarely programmed, or you think that you don't know how to program, you actually have a huge advantage. Okay, that's why we have no problems teaching beginners. The only problems we have are people who are really experienced in other languages and who have never seen or never done anything like in in like Haskell or Lisp or Scheme and stuff like that. All they know is just C++ and Java, or maybe some Python. Okay, so those algol type languages, they focus on loops as a means of transformation. Okay, so I'm sure all of you who have done, let's say, any kind of data science in Python, you are doing a lot of loops, right? Loops and loops and loops and loops and loops. Okay, and that is your primary means to transform data. Okay, and I think Amaldeep Singh, I think he asked me about loops, right? Amaldeep, is that right? The syntax for loops. Okay, that's probably because he wants, that's a natural tendency for most programmers. Where are the loops? Okay, and so my point is, for you to be successful in the kind of programming, there are loops in Smojo, but to be successful in programming with Smojo, for the financial data part especially, okay, you need to stop reaching for loops. Okay, instead, I want you to think of a new way of doing data transformations. Loops are not the only way, and actually there are pros and cons, obviously. Okay, so the cons first for loops is that actually doesn't work well for big data. Okay, loops are harder to write. Okay, they actually encourage poor code reuse. In other words, you find a lot of Python programmers, I find especially, writing the same loop again and again. Okay, or in slightly different forms, right? And I've seen even very professional programmers whom I respect and I worked with as well. When I see their Python code, it looks terrible to me, right? Because it's just loops within loops within loops, and after a while, where the code tends to be very long as well. Can you guys hear me?
Yeah.
Yes.
All right. The other part about using loops is that the tendency is that you will write a lot of code. Okay. So when I mean a lot of code, the reason why you're writing a lot of code is because a lot of the code that you write in these languages are not reusable. Okay. So different languages, I think, have got a different level of how much you can reuse the code. Okay, so Java, I think, is not too bad. So is C++ and this thing, because those are meant for really people who are already coming from a programming background where this kind of stuff is drilled into their skulls. Okay, so if you're a C++ programmer or a Java programmer, I'm talking about like a professional kind of programmer, or you're taking it like on a CS course, then this code reuse is hammered through to you all the time. But I find a lot of people coming from a Python background, especially, this is not drilled into them. And so what happens is that they end up wasting a lot of time because they're writing the same silly piece of code again and again and again. And each time they might make mistakes or maybe slight changes, right? And there's no thought of code reuse. So the lack of code reuse does two things. Number one, it slows you down enormously by a factor of 10 or even 20. Okay. The second part is that without code reuse, you create bugs again and again. And bugs, when it comes to, what is it called? Things like financial data analysis, and so on, are very hard to find. It's not as if your program will work or not work, right? Bugs, when you process data, are very, very hard to find. And that's why code reuse is a very important thing when it comes to data analysis specifically. Okay, so this part of my lecture is not really so much, well, it is actually important also for those of you who are doing the data infrastructure, because you'll be working on this stuff as well, but it's mainly important for those who are doing the financial data engineering parts. Okay, so the loops are good in the sense that they are very flexible. You can do a lot of stuff with loops. Okay, but of course you pay the price. Now, the new way I'm going to teach you, which I think you may have seen perhaps, if you've done some R programming, perhaps you might have seen a bit of this. Okay, it shouldn't be too foreign to you. Okay, so this way of transforming data is called, to apply transformations, is good for big data. It's actually pretty easy to write. I wouldn't say completely easy, all right, but certainly easier than loops, all right. It's very good for code reuse, and you generally write a lot less code, okay? But it does take a bit of getting used to, especially if you are used to writing loops, all right? So the people whom I have the most problems with trying to make the shift are those who are already pretty set in their ways and actually, just want to write loops all the time, okay? Because then your Smojo code looks terrible, it performs terribly, it's hard to debug. Okay. All right. So you need to make this shift in thinking. So now let me just drill down into this a bit more and to flesh it out. Okay. Now there is a problem, of course, with this new way, and it's not as flexible as using loops. So I'm not saying loops are completely bad. Okay. I'm not saying this new way is completely good, but specifically when it comes to data processing, loops are very, the new way of data transformation is actually very good and a very profitable way of looking at things, okay? And you don't need the flexibility that loops offer for these data processing problems. Okay, so the kinds of transformations we are looking at are called sequence transformations, and they have got three ingredients to them. The first is lazy sequences. And really is, what exactly are we transforming? Okay, so we're transforming really lazy sequences or sequences in general. And second is we are going to use XTs and quotations as the transformation itself, right? So what is the transformation will be encapsulated or captured by the XTs and quotations. And last of all, we have something called lazy high order functions. And this is how is the transformation or the XDs, etc., applied to these sequences. Okay, how are they being applied? So these are the three magic ingredients that you have to master over a bit of time. Okay, I'm sure most of you, or in fact, all of you might make the transition quite easily. So let me give you an example. So let's say I have a problem here, and this is of course is a toy problem because I want to make it illustrative, right? Just to show you what I mean by this data transformation or applying a transformation versus writing a loop. Okay, so let's say I would ask you print the kth square. I mean, like a square means like a, you know, like 2 squares 4, etc., right? Which is divisible by 365. So you want to look for all the squares which are divisible by 365. You're going to sort them out. And then you want to divide by the kth cube, also divisible by 47. Okay. And then you want to print the first 100 elements which satisfy of this new list. Now, how would you do that? Okay. So if you have got no programming experience, you'd be scratching your head. Okay. If you have programming experience, I challenge you to just write this code. It's not so hard. In Python or Java or C++ or whatever language you're familiar with. Okay, in loops. Okay, use loops by all means. Okay, as a practice, right, to see where are loops problematic and where are they not. Okay, and I'm using this as an illustration to just show you to flesh out some of the claims that I've made about code reuse, etc. Okay, so this is how maybe a child might approach it. Okay. So the first one is my data is the infinite sequence of integers, like 1, 2, 3, 4 until infinity. Okay, that's my data. All right. You can think of it as data coming from a file, maybe, or maybe data coming from the socket network or something else. Okay, but it's something from an instrument. Okay, so all these things could be potentially infinite. Like a real-time data source is essentially infinite. There's no end to it. Okay. So the first step is to transform this data by squaring the numbers. So for 1, 2, it becomes 2, 4, etc., right? 2, 4, 9, 25, etc. Okay. Then I transform it further by filtering out the elements to capture only those which are divisible by 365. Okay, and obviously the answer is another sequence or series, right? Now, simultaneously, I transform the original infinite sequence of integers, 1, 2, etc., by cubing instead of squaring. And similarly, I filter it by looking at only those things which are divisible by 47. And then I divide these two sequences, and I just take the first 100 numbers and print. Now, this is something that's very simple. It's pretty straightforward. And in fact, it's almost flows from the description of the problem statement itself. Okay, so let me just put this into a box diagram so you can see this a little more clearly. All right, so I have a sequence of numbers 1, 2 to infinity. I pass this, I just square the elements out. Okay, so it's again an infinite list. And I have another transformation down there where I have the cube of the elements. Okay, I filter off the squares for those which are divisible by 365. And for the cubed ones, I filter those divisible by 47. I divide the two sequences element-wise, take the first 100 elements, and then print it out. Okay, I'm done. All right. So try this try this problem we're using loops in any language that you like. All right, so this is the statement again. Now, how about the Smojo code for this? So the first step is to take the infinite sequence 1, 2, dot, 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 and then you square it, and then you filter off those numbers which are divisible by 365. And similarly, you do for the cubes. And then you combine them using a zip width, right? Using element-wise division. You take the first 100 elements, and then you dot list. Dot list means just print list out. Okay, so it's just 4 lines of code. It's pretty straightforward. And the code itself tells you what it's doing. Okay, so I hope you see, if you're not really surprised by how simple this is, try and write the code yourself in Python or in Java, for that matter, okay? Or C++ or whatever language you're familiar with, but using loops. And you can see that's a big change in the way this thing is done, okay? Now, of course, you need to define the word square and cube and div question mark, and we'll come to that. I'll show you how to do that, okay? But they're not hard to do. They're trivial, okay? And this is where the code reuse part comes in. You see, because there's no loops here at all, is there? Okay, so because there's no loops, I can really reuse the code. I can reuse parts of these things, etc. I can make changes quite easily. The changes to make is quite, if I make a change, it's trivial. Okay. Now, I want to talk about an eager versus lazy functions and data structures, okay? Because that's pretty important too. So an eager data structure exists entirely already at the time the program is run. So for example, any data on disk or in RAM would be an eager data structure, okay? And eager functions operate immediately on their inputs. In other words, if you are familiar with most languages, they're all eager, unless of course you are familiar with things like Haskell or maybe some of the lazy iterators in Python and so on, which is not very often used, okay? But most functions in most languages are all eager, and so it is also with Smojo as well. Most of the functions are all eager, but not all of them are eager. Some are lazy. Now, lazy data structures don't necessarily exist entirely at the time the program is run. Okay, an example is one we've done with, just now, which is the infinite sequence. All right, so an infinite sequence by definition cannot exist because it's infinite, right? And lazy functions also, like they are opposite from eager functions, they actually delay working on their input until something called a reduction is called. So in the example that I gave you, the reduction would be the print statement, okay? Because printing, you need to take some elements and actually put it onto the screen. That's what's called a reduction, right? So a reduction takes something that is, it forces all the lazy guys to do their work and actually come up with something that's concrete and in the end, all right? But before a reduction is called, nothing is done. So lazy functions can work with either lazy or eager data structures, it doesn't matter, okay? But the result is always lazy. Okay, now the resulting data structure is always lazy. All right, so there are a few, I would say about, honestly, about 1, 2, 3, 4, 5, maybe 5 of these functions, lazy high order functions that you need to use on a daily basis, okay? Maybe 6. I think SEQ or seek is the only one that you might not use, at least not for the people from the financial course. Apprenticeship, sorry, but mainly for the guys for people on the data infrastructure one. Okay, so you need to be familiar with most of these. In other words, all right. So I will use. I'm not sure you can see this. Chris, is my screen okay? Chris, are you there? Chris,
your screen is fine now.
Okay, you can see the X at the back because I'm afraid it might be blocking or something. All right, so we use the bracket X to denote a sequence of elements Xi, okay? All right, so I'm going to just go through some of these functions quickly. So the function map is very important. It basically takes in a sequence. Remember what the brackets mean, there's a comment. So it takes a sequence and an xt from the stack, and it produces a sequence as an output. Okay, that's what map does. So the xt is any word with one output. Okay, you can have 2 outputs or 3 outputs. It's possible to create an xt with 3 outputs or 4 outputs. But in this case, map requires an xt with 1 input and 1 output. Okay. So in other words, map takes in a sequence and a function f, and the result is a new sequence where that function f is applied to every one of the elements. Okay, but remember, the application is not eager, it is lazy. All right, so this set, so you can easily write a loop and so on, which does this, but the loop will be eager. It will actually run right through the sequence or whatever data structure you have. Okay, whereas map is lazy. It doesn't do anything until a reduction is called. So an example, so 1, 2, triple dot, which is your infinite sequence. I map it with this quotation. This is obviously in compilation mode, right? It's going to double each. It's going to take that quotation on XT and apply individually to each of the elements from 1 to infinity, okay, theoretically. So when I say equal to, I'm saying it's equivalent to, okay, but obviously, like I said, map doesn't do anything until it is absolutely necessary to do it. It's lazy, okay? But the effects would be 2, 4, 6, 8, obviously until infinity, okay? The other one is filter. Filter, you also use it often. And filter takes in a sequence and an XT, just like map, and it produces a new sequence. The difference is that this XT, instead of transforming, is used as a accept. So if the XT applied to the X is true, that that value is accepted, okay, as one of the elements in the new sequence. Otherwise, it is just discarded. All right, it's a Boolean flag. Okay, so sequence takes filter takes a sequence X and a Boolean XTFS. All right, and it only accepts those members in the sequence where fx is true. Okay, otherwise they are discarded. So an example, I've got 1, 2, double dot, which is all the integers, and here the xt obviously that's a 2 mod, a modulus. Okay, so if it's an even number, it'll be 0. In this case, I'm looking for the number to be 1. In other words, it must be an odd number. Okay, so essentially what this is doing is filtering off out all the even numbers. Only the odd numbers are accepted. So it'll be 1, 3, 5, etc. Okay, zip width is the third most important one. And so these three you must already know very well, okay, because you will use them very often. Okay, so zip width, I've got 2 sequences and an XT, and I produce as an output a sequence. So the XT must take 2 inputs and output 1 value. Okay, so I've got zip width XY, X and Y are both sequences. And this time the XT requires 2 inputs. Okay, so it can be like a plus or a divide or subtract. Okay, and it creates a new sequence, single sequence, where it's just the f of xy. All right, I give you an example here, a bit different from the rest. I've got 2 sequences. The first one is infinite. The second one is a finite list. So you can create a list by using the double braces. Okay, so the double brace will give you, in this case, 2, 3, 4, 5, 6, 7. Okay, and here I've used the multiply, integer multiply as my transformation function, my xt. Okay, when I zip width, I will get a finite list. Okay, because I'm trying to zip a longer sequence with a shorter finite one, I will always get a finite list. Okay, takes in a sequence and a number and basically truncates it. You just take the first n values. All right, so take the sequence and number, it give you x1 to xn. That's it, truncates it. So 2 double dot, 1 to double dot, the integers 5 take will just give 1, 2, 3, 4, 5. Okay, it's pretty simple. Take while is very similar, but here we use an xt to know when to stop. Right, so as long as xt is true, the function is true, it will accept. But as soon as it says it's false, it will stop taking anymore. All right? Okay. Any questions before I go to the demo?
Arnold, when you talk about the transformation, right?
Yeah, Keith.
Would this be similar to the pandas dot apply kind of function, where you're just applying a?
Yes, that's right. It's very similar to that. The pandas that apply is a map. Okay, but the pandas.apply is not what I say. It's not a. Is it eager or lazy, Keith?
It's eager. It's eager. Yeah,
It's
I think.
eager, exactly. So when something is eager, it needs to do it there and then. That's the problem, you see. So that makes things like pandas and so on not useful for extremely large data sets. Okay.
Okay, thank you.
Okay. Is this slide going to be shared? Answer is yes. What is GG? Oh no, I have no idea what that means.
No, I think it was we are talking about the use of Smojo, right? Being not friendly for, I mean, disadvantage for those who are already learn loop-based programming.
Well, look, I think it depends on how flexible you are mentally, right? Look, I'm pretty old and I can do this. It's not a problem. You guys are much younger than I am. I'm sure you can do it. Okay, so I was exaggerating maybe just for effect, but I don't think it's a serious thing. It's only a problem when you don't want to make the transformation, the change. Then it's a problem. Okay, so I think it's not so much a capability issue as more of a psychological issue. All right, so Luo Yi asked me, so it's like a Java stream. It's similar. It's similar to Java streams. Yes, a lot of languages are now adopting these things. They're not new by any means. They're actually very old concepts. And there are already languages out there with with parts of these things put in place. Any other questions? Okay, so someone asked me, Ilham asked me, if I would use 1, 3, ... instead of 1, 2, it's basically an arithmetic series, Ilham. So it's 1, 3, ... is 1, 3, and then what's the next number as an arithmetic series? All right, so 1, 3, 5, etc. Be all the odd numbers. Okay, you can write 2, 5, etc. All right, anyone else with a question? Nope. Okay, so in that case, let me just move on to the demo of the coefficient of the characteristic function. Okay, this is it's a simple. Actually, this was a real problem, to be honest. I mean, it actually happened. Okay, and it happened. I forget what's the context. It was I was trying to do some calculation for some kind of electronic circuit. I can remember that. Okay, I can't remember what the context, the original context was. Okay. And I tried initially to just write it in Java. And I thought, hey, it's actually not so simple, right? A function using loops. And then I found a simple solution using what's it called? Using infinite sequences. So just for illustrative purposes, I don't think you'll see this very often, but it's good to just widen your thinking a bit. So can you guys see my screen now? Okay.
Yep.
All right, so a characteristic function is a function like this. Okay, so let's say I've got an f of x, and if it's like one of those polynomials, but it's already factorized. Let's say 2 times, let's say x minus 4, right? Right, x minus 6, etc. Right? Right. So the question now is, sometimes you want to expand this function. You say, look, what is the coefficient of x power 0? What's the coefficient of x power 1? What's the coefficient of x power 2? What's the coefficient of x power 3, etc.? Okay, so that's the problem. The problem is to look for the coefficients to rewrite this. If this were rewritten as, let's say, some C0 plus C1 x power 1 plus C2 x power 2, etc. Right? And Cn x power n. Okay. What will these numbers look like? Okay. Can you calculate these numbers easily? Can you write a program which gives you an input and it just does the calculation for you? Right, so that's the challenge we're going to attempt now. Okay. So I'll put this here. This is called, and this is called, something like this is called a characteristic function. Okay. So we've got the characteristic function. We're just trying to find what are the coefficients of each power of x. Very simple problem. And I encourage you to write this in the language that you're familiar with, just as a practice. Okay? It's a practice. It's a good practice. All right. So the way you're going to do this is to actually use infinite sequences. And but I need to show you a few basic things. So let's say I have a polynomial x. How do I represent it? Well, one way, if I have the p of x, so look at this. This is a p of x, right? I can put a double dot like that, right? So p of x, right? It's like that. Okay, it's a long polynomial. Let's assume it's got no end. All right. I can actually replace this with a sequence. All right, and it'll be C0, C1, C2, until some. If it's finite, it's Cn, and then subsequent entries are all zeros. Correct? Right? So if I have, let's say, px equals to, let's say, some to 1, okay, then in my new representation, it will be just 1 followed by a lot of zeros, right? Okay. Cool. All right. So now with this in mind, what I'm going to do is I'm going to say that let's break this problem down a bit. Okay. If I have a polynomial then, and if I multiply by x, what happens? So look at this. This polynomial here, let me undo this. Sorry. Let's say I have an x times p of x. All right. Now, p of x is just this number here. Let's say whatever else it is, right? This is p of x. Let's say it's infinite. We don't limit it. Okay, we don't say it's finite, infinite. We don't care. All right. Now, this is p of x. But if I multiply this by an x, what happens to all these coefficients? They're going to be shifted down by 1, right? So it'll be 0 followed by C0, C1, C2, etc., right? Correct? Right? So in other words, all I need to do, and I multiply any polynomial by an x, if it's represented this way using an infinite sequence, is just to append 0 to the front. Okay? So I can say, so any, I'll call it mul, or mul by x, okay? And I want to put a sequence. I'm going to have an output sequence, okay? So each time I multiply any input polynomial which is represented by a sequence by an x, all I'm going to do is to append 0 to the sequence itself, okay? And the way you do it is use something called cons. So it's 0 cons. All right, so 0 cons will take that 0 and put it right in front. It concatenates or conses it right to the top. Okay, that's not so hard to do, right? To understand. What it does is it takes something like this and it transforms it to something like that. All right. So far, so good. Okay. Now, how about if I multiply by a number this time? Instead of multiply by x, I multiply it by a number. Okay. So in other words, I have my px again here. I have my px represented this way. Okay. And now I want to multiply by some, let's say some number a times px. All right, so you can see quite clearly, all I got to do is to multiply each element of this what is it called, of this sequence by A, because it'll be A times C0, A times C1, A times C2, etc., right, to infinity. All right, and to do that is also pretty simple as well. All right, remember what I talked to you just now, that is called A, so I'll call it mul A, right? Okay, now here I've got my sequence, okay, but I also have some number A as well, and it's going to have a new sequence. Now, for reasons I'll explain later on, I'd prefer to put this A in front, okay? So I'm going to bind this to an A, okay? And here, what I'm going to do is, because the sequence is already on the stack, I've only bound the A, okay? I'm going to create a quotation here, which is A times, I'm going to map it. That's it. All right. So given, and what this does is, given a sequence and an A, it's going to take that sequence and multiply every element from the first to infinity with an A. That's what A star map does. This is the XT. Remember what map does? It takes the XT and a sequence in the bottom of the stack and then applies it. Okay. Now, with mul X and mul A, I can already start to write this guy here. Okay. It's not so hard. So first, I start off with just Px equals to 1, all right? Because something like this is really an iteration of multiplying stuff by from 1, okay? So I start with, so I'll call it characteristic, all right? And here, I'm going to have an input sequence, which represents these numbers here, this, etc. Okay. So the input sequence is the what is it called? Characteristic. What do they call roots? Right, because these are all roots, right? These numbers are all roots. If x equals 2, for example, this whole fx, it becomes 0. That's a root. Right, so it's the roots. Okay, and I'm going to give you another sequence. All right, and this other sequence is what is it called? The output. All right, that you need to actually print out. Okay, so this output here are these numbers that you're going to get. How you have C0, C1, C2 until Cn. Okay, so let's see how this is done. So remember, this sequence here represents all of these numbers here. All right, that's the inputs. Okay, so I'm going to start off at the very start with Px equals to 1. Okay, which we know. Why is that? Because you're going to start somewhere. Okay, and I have this input sequence, as an input polynomial. I'm going to apply this mul X and mul A many times to it. Okay. So here, this, as we know, to represent it, it will be 1, 0, 0, 0 until it goes to infinity, right? And the way we write that is just, we first construct this part here first, which is 0, 0, dot, dot, dot. That's infinite number of zeros. And then we add a 1 in front. So it's 1 const. All right. And that's your first starting point. Okay. And I'm going to bind this temporarily because it's not so clear, just to SS as my input. I'll call it XS if you want to. Or CS's, C's. Okay, since they're all the C's. Okay. So I have this on the stack. It's an infinite sequence with 1 at the start and zeros all at the back. And it represents the number or the polynomial Px equals to 1. Okay. Now I have the list of these sequences. What do I need to do to transform this guy? Remember, think of data transformations, okay? So that I can multiply it like that with one factor. So I need to find out what the factor is, then run the multiplication, correct? So I'm going to have a function here called mul by factor, mul, right? And this, all I need to have is my sequence, a number n, okay? And I'm going to just leave a new sequence on the stack, all right? And this represents x minus c, oh sorry, I'll call it, by convention, we did a minus sign. Yeah, we can use a minus sign if you want to, but tell you what, let's change this to positive signs. Oh, okay, minus. So just multiply by x minus c. Okay, x minus c times p of x. Now you know that that's the same as what? That's the same as x times p of x minus c times p of x, right? So you can see this part we already did because it's already here. It's mul x, this is xpx. And this part here we already did, all right? Because it's here, right? This part here, okay? Whether it's A or C is a naming convention, okay? So I'm gonna just, I'm gonna take the, what is it called? I can bind this if I want to. I call it px, a ps, and I call it a c. Okay, and then here, I'll tell you what. Just for yeah, I think I'll have to do it this way. I'm gonna call it a instead, right? So these are all the a's. Okay. All right. So I need to take the ps and the a, and I need to put mul x first. All right, so that gives me the first part here, this part of the term. And then I want, this gives me the first sequence. This gives me xpx. And here, I'll take px, sorry, sorry, my bad. Mul x has got no inputs apart from the ps. There's only one sequence input, right? And I have ps a mul a, and this is a px. And then I want to subtract these two sequences. Remember what we did just now with the zip width. All right, this is a case for zip width. It'll be a minus sign zip width. Okay. All right. So here, I've got my base sequence here. Okay. That's the basic sequence I already have. I'm going to apply each of the elements here with mul factor, right, one by one, right? So how do I do that? I got my CS, and here I have, I just call, in fact, all I need to do is just to call in, what's it called, mul factor, all right? And I can call map. Okay. So what this does is it takes these guys, or in fact, I don't even have to call map. I could call reduce if I want to. I think reduce. Yeah, because CS is finite, I can call this reduce. So it will then do it a finite number of times. All right. And it'll multiply all the factors. And the output is, because this mul factor is sorry, it always produces a sequence in the end. Okay, so the answer here will be a sequence. Okay, so now I've done all this stuff. Let's give it a twirl around and let's just see what happens. Okay, so I've got here the example. Let's do 2, 4, 6, 8, 10. Okay, so the factors are 2, 4, 6, 8, 10. Okay, I'm sure I got a bug somewhere. Okay, characteristic, how do you spell that? Okay, so then here, I need to be careful because the answer here is an infinite sequence, right? Because it'll be number until the last n here, and then it'll all be zeros, right? So I don't want to take too many. How many should I take? Well, if I've got 1, 2, 3, 4, 5 here, the highest power will be x power 5, right? But I will have +1 numbers, right? So 1, 2, 3, 4, 5, x power 5, but I have a x0, which is a constant. So it'll give me 6 numbers altogether, all right? X power 0, x power 1, x power 2, until x power 5, that's 6 numbers, all right? So with 5 here, I get 6 numbers. So I put 6 take dot list, right? And I hope this gives me the right answer. It's very embarrassing for you guys as well. Oh, I'm sure I made a bug somewhere. Okay. All right. So when stuff like this happens, which it always does, okay, what you got to do is you have to do something called a debugging. Okay. So the question is, where did we go wrong, etc. Right? All right. So let's see now. Okay, so let's take a BP out here. So a BP, what it does is it just shows us the state of the stack. Okay, let's see if the function did produce anything at all or not. Well, it did not. Okay, and let's try. So we got CS out here. Let's try here, BP here, and see if that worked. Oh, I see. No wonder. I have all these things uncommented. Sorry. Okay, so let's remove all the BPs again and let's retry it. Okay. So you guys can check that this should be C power of, I think, 0. Okay. Sorry, this is C power of 0. Yes, so it'll be, this one here will be 2 times 4 times 6 times 8 times 10. Can someone just do the math?
Yeah, it's correct, Arno.
Okay, but this one here, 1, doesn't look quite right to me. Why is it 1? Oh yeah, it is 1 because...
It'll be 1, right? They're all no coefficients.
Correct, it'll always be 1. Correct, no coefficients. Right, so it's very easy, right? Not that hard, right? Okay, you can see the amount of code that we did was not that a lot. Okay, but this is a simple, but I think a little, honestly, a little contrived example of how you can actually use these infinite sequences for just run-of-the-mill kind of programming. Okay, but in all honesty, this kind of using of zip width and map and so on is actually very common. Okay, and the use of laziness is very useful because you don't have to care about the end of something. When you are using a loop, you always have to care about the end. What is my end? What is it called? You know, thing, right? What's my end? When should I stop? You can't write an infinite loop because it'll just go out there like crazy, right? Spin its wheels. So the only part of this whole calculation where we have to find out what the end is this part here. Okay, and where is the reduction, Keith?
The reduction is in the reduce? Oh no, as in...
Okay. The reduction here is not really a reduction because it works on CS, which is finite.
The reduction is what is called before the lazy function will run, right?
Correct. So you can see up to this. So is characteristics lazy?
I would say yes.
Yes, it is. Okay. This reduction here works on the finite input. It doesn't count. Okay. The 6 take is also lazy as well. So reduction is really here in this part, in the dot list part, okay, which is the printing out of things. If I do a BP here at this point here, you can see it does nothing at all. It will show you that it's just a tick, okay. So if you're, in case you're wondering, why is it terraweather.mini, right? So because the original name for Smojo was Mini, but unfortunately Mini was trademarked with a car, right? So we couldn't call it Mini. And TerraWeather is the company that we belong to, which this was originally developed for, okay? So, and the take here is basically a Java object, okay, which is a lazy, it represents a lazy, what is it called? A lazy sequence. All right. Okay, I must admit that this example is a little subtle because, I mean, if you've never seen something like this before, it can be a little worrying, right? So it's not so worrying because most times the examples are much simpler, and you'll be working with finite data as well. Maybe if you have a time, I'll do an example where we work with some finite data and give you an example of doing this, but with finite lists. Okay, any questions? I'll just stop here for a while. Any questions? Chris, you need to help me, man, because I can't see the chats.
Is there a way to get the length of a finite sequence? The best I've done was just tailing sequence until it's empty.
Okay, so yeah.
From Daniel, yeah.
Yeah, okay, Daniel. So the way you do that is, let me just open up a new page here. So let's say I want to call length, right? I can't call it length because length is already a word for the length of a string, all right? And I call it a sequence, and it's going to give me a number, okay? And let's assume that it's always finite. So say, hey, you know, warning, right? Okay, must be finite, all right? And honestly, there's no way for you to tell whether it's finite or not. Okay, and only the programmer knows because that's the way he programmed the whole thing. Okay, so the way you do it is to basically say you first put 0 on the stack. That's your counter, so to speak, your counter variable. Okay, and then you call it. It needs to be a reduction. Okay, but this function, so I'm going to call it reduce. All it does is to drop whatever is being fed to it and call the 1 plus. Okay, so this is one of the simplest ways in which you can actually do a finite length sequence. And no matter what language you do, you'll be doing something very similar. Okay, you have to traverse the linked list. Internally, it's actually a linked list of some kind. Except, of course, for those which are lazy, then it's not a linked list, right? It's partly linked and partly not. So like this, for example, if I have 1, 2, 4, 5, 6, 7, len, right? The answer would be, oh, so let me get this somewhere.
I think you have to dot after the plus, right?
Sorry. Here it needs to be the sequence, right? But I put a 0 here, correct? So I need to swap the places around, correct? So swap means that if I've got, let's say 1, 2, I call a swap, that would be 2, 1, okay? So here, right, because the reduction, remember it, okay, reductions, I didn't explain reductions. I think it's something I missed on the slides. I apologize. Reductions or reduce, sorry. It takes in a sequence and an xt, and it produces, we don't know what, okay? Because there's no, the output here depends on the output of your xt, basically, what it's doing. Okay, so we denote that by a star. Okay, so reduce does, but it needs it in this order: a sequence at the bottom, and then the second one, it must be an XT. Here, I put the 0 here, so I need to swap places with the input sequence. So now if I run this now, it will run fine. Okay. Next question. Chris, any
I
question?
didn't think of using reduce because I needed the length of sequence to implement a reduce.
You shouldn't implement reduce. If you try and write functions like this in Smojo, it will be much slower than the built-in versions. If optimize the built-in versions. Any other questions?
I think we don't have any more questions, but oh yeah, any other questions?
Yeah, so is there a way to generate sequences other than arithmetic sequences?
Of course. In fact, you'll be doing that to death later on. Okay. But they involve data sources. So I didn't want to clutter the conversation with what is it called? All the other, mumbo jumbo to get that data out. But the answer is yes, obviously.
So more specifically, is like I know other languages have like a way of generating sequences where you specify the first element, then you specify the function that generates the subsequent elements, like some kind of iterate type of sequence generation. Is there something like this here?
Yes, there is. It's what I didn't explain to you. It's called SEQ. You can do that, yes.
So you can actually specify a start
okay.
element and then an XT.
Let me give you an example. Okay, I'll type out the example. Okay, it's a good question. I'll type out an example. So a place where this might be useful are things like, random number generation and so on, right? So if you're familiar with that kind of stuff, a simple one would be a linear congruential generator, LCR, okay? But I won't use that. I'll use something very simple. Let's say if I start with something like a 0 as my starting point, okay? And any kind of function, each time you call it, gives you a different answer, must be stateful. Isn't that so? Right? So by definition, it needs to store that state somewhere, right? So in this case, we will call it number, or what do we call it? Or num, okay? So this assigns 0 to num. You can do it this way, or you can call it a variable. All right. So the starting value for num is 0. And I'm going to call my function my func. All right. And all it does is to produce some number n. Okay, because if you want to make a function to a sequence, you need to obviously it cannot accept input. It needs to just output the number all the time. Okay, so this could actually be also coming from a file, or it could come in from a, let's say, it could read it from a, what is it called, a socket, or you could, let's say, read it from an instrument from your, let's say, from IO port or something else, right? There are many ways you can do this. This is a trivial way of doing it. And all I'm going to do is just to take the num, and I'm going to, let's say, I'm going to add it with the time. And I'm going to randomly, let's say, mod it. So I'm going to say 365 mod. Okay, that's my new number. So now will give me the current time in milliseconds. Okay, I'm going to add these two numbers together, and then I'm going to call 365 mod. In other words, it will give me a number from 0 to 365. Okay, and I'm going to take this number as an output, but I'm also going to store it as an input as well. Okay, so I'm going to say, I'm going to duplicate the number. I'm going to duplicate. Dup means duplicate. Okay, and okay, my apologies, because it's a variable, I need to call the fetch and num store. Okay, so this, because it's a duplicate, I have two copies, one in which I store into num and the other in which I spit out to the outside world. Okay. And here, all I got to do is I got to tick my func seq, and that creates an infinite sequence from this. All right. So I put, let's say, 100 tick dot list, and then it's done. Where did I get wrong?
I think you have a typo at the my func.
Yeah, that's right. Okay. So this is a very bad way of generating random numbers, so don't do it. Now, if we didn't want to use this one here like that, or we can call it something else. Let's say if I had done it this way. And I just output that alone. You wouldn't get, I think, as a nice a list as this. Oh, my func, oh, plus, sorry. Yeah, see? Okay. So this is a bit better. This is more like a linear congruental generator in a way. Well, not quite, but similar idea. Okay, does that answer your question?
Yes.
Right. Okay, anything else? Any other questions? So seek, by the way, takes in an xt and assumes that the xt is going to spit something out. It doesn't have to be a number. It can be anything, to be honest. All right, it can be even a function which spits out other functions. Then you get a sequence of functions. It can be a function that spits out a list, then a sequence of lists, right, etc. Okay, any other questions, Chris? Otherwise, I'll move on.
There's no questions.
Okay.
But I think we have to be mindful on time as well, right?
Yes, I have just the last part and I'm done. Okay. All right. So I had this thing for the class. Sorry, you can't see my screen. There's one thing I wanted to do, which I didn't have the time. And that is that now, okay, look, so now I've got this my func word out here, right? And it's nice. But let's say I want to share it with you, with all of you in this chat here, all right? The way I do it is I convert this semicolon to semicolon dot.
Can you share your screen?
Oh, my bad, sorry. Okay, so if I want to share this my marvelous number generator with you guys, I just call from semicolon, I put semicolon dot. Okay, and that publishes, if I run this time, it not just runs it, it will also publish it to the Smojo cloud. Okay, so this is something that you need to be aware of because it's quite different from other languages as well. So here, even if I close this out, all right, and if on here, I click in Arnold, my func, right, and I put, let's say, 10 tick dot list, and I put the control R. Sorry. Oh, sorry, my bad. I wrote it wrongly. I forgot to put the sequence inside here. How do I do this? Shucks. Okay, I should have put the sequence in before I did that. Okay, we can sort of like salvage this by doing it this way. Okay. Okay, So what I'm trying to tell you guys is that I should have wrapped this up properly for you all to test out. All right. I should have called it something like, maybe I put this in instead. Okay. Then, okay, now if I do that, then the new one is called test. Okay, let's not fuss with this. But my point is that I should have wrapped it up just now properly. No, I did it correctly. It's just that this part here is wrong now. Okay, now if I do Arnold test and take dot list, I think I should get a better result. Where did I cock up? Sorry guys, I think I must have messed it up somewhere just now. All right, but you can actually save these words to the cloud. So whenever you're doing something, you can actually save it to the cloud, and then you can recall it later on. We use it actually very often for doing stuff. And if you are in the infra development, you'll also be doing it as well. Okay, if you are in the financial data one, it's not so important for you to know. Let me just close this stuff up. Okay, one last thing I need to share, and then I'm done. And that is, can you guys see my screen? Sorry.
Yep.
Okay, so I've done that. So there are a few things that you need to do in good Smojo. And that is the words are normally very short. So far, all the examples I've shown you are pretty short. And typically, your functions are usually 1 to 3 lines long at most. Okay. And you compensate by using many short words. So the idea is that you're testing it small pieces of code. Okay, so when I wrote the function for the characteristic function, for example, it was quite short. I could test out each piece separately and then glue them together in larger pieces of code. What you shouldn't be doing is write a lot of code and then test towards the end. Don't do that. Write a bit, test a bit, write a bit, test a bit. You find yourself extremely productive that way. Okay. Sparingly use local variables. You really, especially for those from I think Java/Python or any other language, right? You would use a lot of local variables, and I find this is a huge hindrance. You normally don't have to do it if your functions are very short. So if your functions are more than 1 to 3 lines long, maybe something is wrong. Okay, maybe the way you're looking at the problem is wrong, or it's suboptimal. Okay, try splitting it down. So it's not a hard and fast rule, but it's just a way for you to have a feel for what is going on, right? So the 1 to 3 lines long is just a guideline. And if it's longer, if you're writing like 10, 12 lines in a piece of code, unless it's for a very specific reason, it's probably wrong. Okay. We rarely use explicit loops. Now, we've been programming in Smojo now for years. Okay. Not just 1 or 2 months, it's years. And like I said, we've written a lot of code, a lot of all the AI stuff at the back end is written in Smojo for the front part layer. We very rarely use explicit loops. You probably don't need to use it, even for the infra development, surprisingly. You want to use multiple definitions of the same word to lay in functionality. I thought I had the time to explain this, but I don't tonight, unfortunately. But I'll give you some notes later on to supplement this part. And you really do want to look at creating your own library of words that help to solve your problem domain. So like I said, especially for the guys in the financial data engineering, don't reinvent the wheel each time, because each time you do it, it slows you down, it becomes buggy, and you're wasting your time and everybody else's time, your teams as well. And everything else slows to a crawl. What you want to do is to create a library of words that you can reuse again and again, your go-to little notebook, right? And then, for that niche. All right, so that's the way we try and program in Smojo. Okay. You can, I'm sure a lot of you are asking, are there like libraries we can use and so on? Yes, of course, there are libraries you can use, and there are many out there, because Smojo very easily interfaces with Java. Okay, the integration with Java is trivial, and you can do it within Smojo itself. But because what we're doing is pretty novel as well in some ways, and I want you guys to have the feel of developing stuff yourself and doing data transformations, and you don't have to do too much, to be honest. Okay. All right, guys. So that's the end of today's short talk, I hope. I will send you guys a list of homework, not too much. Okay, Chris will split you up into teams. Right, Chris?
Yep.
Right. And then you can hand in your homework towards the end of the week. All right. And if you haven't got that agreement signed, please do sign it ASAP. Chris will probably remove those participants who haven't given us the agreement form, because we need those in order to bring you on board. And I don't want to delay this any further than it can be delayed. All right. So unless there's any questions, okay. Anyone else has a question?
Yes. How to remove or edit my word from cloud?
You use the word remove. So remove space the word name, and it removes it. To edit it, you can just redo it, or if you want to edit it, just redefine it. It'll be fine. Any other questions? Okay, Daniel. If there's no questions and you can think of something over the week, feel free to just drop it in the Telegram group, and I'll be happy to just answer your questions. Okay. And I will give you a quick peek of next week's syllabus. For the financial data part, we're still ironing out some things. There's still a lot of work to be done on our side for other stuff. But we already have the syllabus. I just need to write it up for you. For the infrastructure dev, we already have all the syllabus done for you already. So that one needs to go up online. We're still preparing the backend, Sam and I. And I hope we can get everything done on time by next week. So next Monday, we will have a short talk. Sam will give the short talk for the infra development. And on next Wednesday, I'll see the guys from the financial stuff, right? So we purposely planned that way because we know that most of the guys from people from infra dev are all probably already very good programmers. So you shouldn't have a problem with this kind of stuff. But for the financial data engineering, it's a wider background. I want to give you a bit more time, and also for this stuff to sink in, and for you to practice. Okay, so practicing is the key, right? So just after this, we will share the slides with you, and I hope I will also give you a list of homework that you can work on immediately if you have the what is it called, the access. And I will also then put out later on, what is it called? A couple of problem statements that you can work on. Okay, it is not difficult. Okay, maybe one or two that you can work on, and really that is just for you in teams, obviously, for you to really flesh out this understanding. All right, so good night, and that is really all that we have for tonight. Thanks.